Okay guys, so this is where we start designing powerful closed-loop controllers. I'm sure most of you will have heard about PID control. Well, the P in PID stands for proportional, and this is what we are going to look into in this lecture. What is proportional control? Let's first have a look at this block diagram. Most of you should recognize it by now. It is a closed loop block diagram. So you can see that you have an output yt that comes in with a reference signal rt. Yt is then subtracted to rt to create the error signal et. This error signal is fed to the controller. In this case, the controller is a gain kp. So in a block diagram, when you have a triangle, that triangle represents a gain. A gain is effectively a multiplier. So the control signal here, in the case of a proportional controller, is actually ut is equal to kp, which is the gain of the controller, is the variable that we set, multiplied by the error et. So essentially, proportional control scales the input, which is ut in this case, by a value that is proportional to the error observed. It is easily realized electronically using operational amplifiers. It is essentially a multiplier and is very useful for speed control. Again, there is no better way to understand engineering concepts than to use them in examples. So here we're going to have an example of how we can use proportional control. We have the following planned function. GPS equals 93.6 divided by s plus 1.95. It's actually quite a simple transfer function with only one pole. We need to determine the proportional gain Kp in order to obtain a settling time of Ts equals 0.2 seconds. So we need the response of the system to settle in 0.2 seconds. We will also find out the steady state performance of the system. The first thing we need to do here is determine the open loop transfer function of the system. The open loop transfer function is essentially the controller's transfer function multiplied by the plant's transfer function. So here the open loop transfer function is gs equals kp times gps, which is equal to kp times 93.6 divided by s plus 1.95. We can also write the equation for the error. So the error is es equals rs, the reference, minus ys, the output. But we know that ys is equal to gs, which is the open loop transfer function, multiplied by the error es. So we have that the error es is actually equal to rs minus gs times the error itself. We can then factor that and divide through, and we get that es divided by rs is equal to 1 over 1 plus gs. And this is the closed loop transfer function of the system. It gives the error with respect to the reference input. So we can plug in the numbers and we get that the closed loop transfer function of the system is s plus 1.95 divided by s plus 1.95 plus kp times 93.6. We now need to determine the closed loop characteristic equation of the system. We know that the closed loop transfer function of the system es over rs, so essentially the transfer function between the error and the input, is equal to 1 over 1 plus gs, gs being the open loop transfer function of the system. The characteristic equation is essentially the equation that tells us a lot about the behavior of the system. So from this, I'm sure you can guess that it is essentially the way to find the poles of the closed loop transfer function. So the closed loop characteristic equation is actually 1 plus gs equals 0, which is the denominator of the closed loop transfer function equal to 0. So we can plug in the numbers again, and we get that the closed loop characteristic equation is actually s plus 1.95 plus kp 93.6 divided by s plus 1.95 equals 0. Now for these to equal 0, the numerator has to equal 0. So the equation becomes s plus 1.95 plus kp 93.6 equals 0. We now want to find the specifications of this closed loop transfer function. Any standard first order transfer function like we have here can be written in the following form. The numerator contains s minus z1 being a 0, and the denominator contains s minus p1 being the pole. We also know that the time constant is given by t equals minus 1 over p1. Again, p1 is the pole, and the big T is actually the time constant. By definition, the settling time is 4 times the time constant. So all these are just given. It's part of the theory. You can just learn this by heart, or you will always be able to find it through some resources or through my lectures. So again, the time constant is minus 1 over p1, while the settling time, which we are trying to design for, is actually 4 times the time constant. So for a settling time of Ts equals 0.2 seconds, we need to have that the time constant is equal to 0.05 seconds, simply because Ts is equal to 4 times the time constant. We also need P1 equals minus 20, again, because we know that the time constant is equal to minus 1 over P1. So with all this, the characteristic equation becomes s plus 20 equals 0. We can therefore write that the characteristic equation that we found before must be equal to that characteristic equation that we want to have in the end. So we can write that s plus 1.95 plus kp 93.6 is equal to s plus 20, itself equal to 0. If we develop all this, we can actually find a value for the proportional gain of the controller, that is 20 minus 1.95 over 93.6 equal to 0.193. And finally, we can rewrite the closed loop transfer function as Es over Rs is equal to S plus 1.95 over S plus 20. We can now find the steady state error of our system. So we saw before that the steady state error is actually the error that remains between your final response of your system and the desired reference you want to reach. Okay, so essentially in mathematical terms, it is the limit of the error with respect to time as time goes to infinity. Well, if you apply a Laplace transform to this in the S domain or Laplace domain, this is equivalent to S multiplied by the error with respect to S as S goes to infinity. We can then use our closed loop transfer function that we just calculated to replace the values, and we get that S multiplied by S plus 1.95 divided by S plus 20 multiplied by Rs as S goes to 0 is equivalent to the limit of the error with respect to time as time goes to infinity. Another thing that we know is that R with respect to time is actually a constant C. Well, the Laplace transform of a constant C is C over S. So Rs is equal to C over S. If you plug that back in the equation, you will get that the S which divides the C in the equation Rs will cancel out with the first S in the equation for the limit. So eventually, you get that the limit of the error with respect to time as time goes to infinity is equal to s plus 1.95 divided by s plus 20 multiplied by the constant c, because the two other s's that were present before cancelled out, and all this as s goes to 0. So s going to 0 means that you can get rid of the s. You get that the limit is equal to 1.95 divided by 20 multiplied by c, and this is equal to 0.0974 c. So eventually, with our proportional control, in an infinite amount of time, the error between the response of your system and your reference input will always be equal to 0.0974 c, c being actually your reference input. And this is a consequence of proportional control. It is very, very hard to get a perfectly zero steady state error, simply because proportional control doesn't actually look back on your error. It doesn't know your long-term error. It reacts to an error that is happening right now. So as this error gets closer to 0, the proportional control actually reacts less and less, simply because it scales by a constant value that is your proportional gain, that error. So imagine that the smaller that error becomes, the less the proportional control is gonna act, until the error is so small that the control does not act anymore, and so you keep that error forever. So in the end, proportional control is simple and very cheap. Why is it cheap? Because first of all, it costs nothing to just add a multiplier in a line of code. It's also very easy in electronics. You just put an operational amplifier in, which is literally a piece of circuitry that's extremely common and cheap. However, the problem with proportional control on its own is that it can result in a non-zero steady state error. Why is that? Because essentially, as we just saw, the proportional controller only acts on the current error. And that error is going to progressively get smaller and smaller as the proportional control acts on it. But however, at some point, the error is too small for the proportional control to have any effect, because the proportional control is just a scaling of that error. So in the end, on the long term, the error will reach a too small value for the proportional controller to have any effect anymore, and that error will remain the same. Proportional control can also give unsatisfactory transient response, simply again because it acts on the current value of the error. It does not see in the future like a derivative controller will do. We'll explain why later. And it does not see in the past like an integrator actually does. So it leaves it lacking, but it's also the most simple way to implement a feedback control loop or a closed loop control. If you were to compare it to a mechanical component, a proportional controller is actually a spring. If the error is too large, it will immediately pull back on it to make it smaller. But if the error is too small, then the spring will barely move and won't be able to compensate for that error. So this is it for proportional control. If you guys need any additional explanations or you need any help with something specific, please do not hesitate to message me. I'll be very happy to help you.